All right, so as you may know, USM elevated their COVID status, so I was kicked out of my office on campus, so I'm doing this from my house, and I don't vouch for my Wi-Fi. Hopefully you can all hear me. This webcam, I'm pointing it down towards a piece of paper, and as you may notice, it's having like trouble auto-focusing. So this, you'll have to give me some feedback if this works or not. I was messing around with it earlier, and it I don't know, it seems sort of dicey. If it's too distracting, I'll try to move one of my whiteboards from my office back to my house for Wednesday, but you'll have to let me know. So we're going to focus today on the crossed Aldol reaction, and specifically the issues involved in that. The number of products that you get is a crazy number of products. So let's go ahead and start. Hopefully you can all hear me if my voice is clear. If not, just chat, type something in the chat function, or unmute yourself, and hopefully I'll be able to hear you. Okay, so I think last time we left off looking at ethanol, doing a crossed aldol with propanol. And again, this thing is going to like do this crazy autofocus thing. So I apologize for that. So let's look at this under base conditions, sodium hydroxide and water. And basically the issue here is that we have two different aldehydes. So ethanol, propanol. So we have an alpha carbon here, we have an alpha carbon there. And so what this system is going to do is a series of different aldols. We have no control over the product distribution at this point, in which we have self-aldol condensation of ethanol, which I believe we saw already. We'll have self-aldol condensation of propanol, and then what we're going to have is crossed, where this reacts with this, and then that reacts with that. So what I want to do first is set up a series of columns here, and then we'll look at the products that are formed and why this is so complex. So let me put in the first column, I'll write the word electrophile. The second column, I'm going to write the word enolate. And the reason we're doing this is to just keep track of all the products that can form. So let's do the self products first, because those are the most, I think, straightforward. So here I'm going to write self. Then I'm going to use ethanol as the electrophile. So it's acting as the electrophile. This is going to be the new beta carbon. Then the enolate is coming from ethanol as well. So we're using sodium hydroxide as the base. It's going to generate the enolate of that. So here's our alpha carbon. This is going to be the new beta carbon. So this will collapse. To attack that carbon. The product will be, again, the aldol product. I'm going to draw the final protonated thing. The beta hydroxyaldehyde. So here's alpha, there's beta. Again, we're starting at oxidation state 2. It then goes down to 1. So again, this is a beta hydroxyaldehyde. That's a typical aldol product. So we're forming one stereo center here at the beta carbon. So we have 2 to the 1 equals 2. And again, that's going to be a 1-to-1 mixture of R and S. Now let's go ahead and look at the self-condensation of propanol. And again, just so we're all on the same page of why we're doing this, if you take an equal mixture of ethanol and propanol under these conditions, you cannot control which one forms the enolate, which one acts as the electrophile. So you have to look at all the combinations. So here's our electrophile propanol. If we form the enolate, so this is something you should be able to do, is look at a carbonyl containing compound and just draw an enolate from it. This specific enolate, as I've drawn it, if we consider the alkene has geometry, and we're looking at this sp2 hybridized carbon and we give it priority, methyl versus hydrogen, this would be 1. Then we have oxygen versus hydrogen, so that's 1. They're on the same side of the double bond. So this would be considered a Z or cis enolate. And that adds to the complexity of this reaction, why it produces so many different products. So again, this will end up being our beta carbon. Here's our alpha carbon. When this collapses, the alpha carbon attacks. So that beta carbon is reduced in oxidation state. There's our product of that self-condensation. So we have alpha, beta. Now in this case, we have 1, 2 stereo centers. So we have 2 to the 2 equals 4. So when this undergoes the self-condensation, we end up with 4 possible stereoisomers. We'll go through the analysis of those on a separate sheet, but now let's just go through the 2 crossed variants that can happen. So let's keep this in mind. We'll revisit what those 4 stereoisomers are. So one of the cross scenarios that can happen, let's use ethanol as the electrophile. So it's accepting the electrons from the enolate. Then let's go ahead and use propanol as the enolate. Just for variation, I'll draw the other geometry. So if we do that same analysis, we have carbon and hydrogen. This would be 1. Oxygen, hydrogen, this would be 1. They're on opposite faces of that alkene. So this would be the E enolate. Again, even though I'm showing only 1, when you do this reaction, you form both the E and the Z. At this point, knowing what we know, we cannot control that. So here's our alpha carbon. There's the beta carbon, which goes from oxidation state 2 to 1 in the product. So there's the alpha, there's the beta. It's now been reduced from 2 to 1. We form a new stereogenic carbon there, new stereogenic carbon there. So we have 2 to the 2 equals 4 stereoisomers for that as well. So if we look so far, we have 2 plus 4 is 6, plus 4 is 10. So just with these three that we've looked already, we can form 10 different products in this reaction alone. Let's look now at the other cross variant. We're going to now use propanal as the electrophile. That's going to end up being the beta carbon. We're going to use the enolate from ethanal, now in this cross variant. Notice that this enolate here does not have any geometry because these are both hydrogen. So there's no E or Z geometry for that. So what that means at this alpha carbon, there's no stereogenic carbon formed in the product. So here's our beta carbon. This is the bond we just formed right here. There's our alpha carbon. There's the two H's, so that's not a stereogenic carbon. Only the beta carbon is. So we have 2 to the 1 equals 2. So let's do a count here. We have 4, 4, 8. 2 is 10 plus 2. That gives us 12 total products. So I'm using the word products pretty general here. Of course, in here, this scenario, they're enantiomers. In these two scenarios where there are 4, we have two pair of enantiomers. And again, we'll look at a separate sheet of those. And again, here, these are enantiomers. So the relationship of all 12, we can't really say all of them are constitutional isomers or anything like that because they'll have different molecular formulas between them. We can just look at the pairs, self, self, cross, cross. What are those relationships amongst themselves? Any questions so far? Can you all still hear me all right? It looks like positive responses. Okay, so just to recap this before I move this slide over. A crossed aldol is when you have two different species that can each form enolates. You're under conditions that will not control which one forms the enolate or which one forms the electrophile. So you look at all the possible scenarios. In this case, we end up with 12. And what I want to do now is look at, actually, let's look at, we're going to look at the stereochemistry of this particular reaction where the ethanal is acting as the electrophile, the enolate is coming from the propanal, and so we'll look at these. I want to draw all of these 4 out so you can see the relationships amongst them, and this will be a review of the Newman and Fischer projections as well. So this will be the stereochemistry of the crossed aldol. So let me just rewrite that specific one so we can refer back to it. We're going to use the ethanal as the electrophile plus the propanal as the enolate. So there's alpha, there's beta. Those are the two stereogenic carbons. And again, that is the new bond that's formed. It's always between the alpha and beta carbons. So let's go ahead, and I'm going to arbitrarily draw one of these first, and then we're going to look at its enantiomer. Then we'll look at the diastereomeric pairs. So all I'm doing is taking this, and I'm going to be putting wedges or dashes here and here. So let me just first draw in the carbon backbone. This is 1, 2, 3, 4. The aldehyde is at the highest oxidation state. This carbon's at oxidation state 1. So it's going to be named as an aldehyde. So we have 1, 2, 3, 4. So it's going to be a butanal derivative. And so what I was just doing is determining between this oxidation state and that one, which becomes the parent. 2 is greater than 1, so the aldehyde becomes the parent. So if we finish naming this, we have carbon 1, carbon 2, carbon 3, carbon 4. So we have substituents at, we have a 2-methyl and a 3-hydroxy. So not considering the stereochemistry, which we're going to determine here, the name of this would be H before M. So 3-hydroxy, 2-methyl, butanal. So that's the parent name, and now what we're doing is determining the stereochemistry to determine R or S at each position. So for the first one that I'm going to draw, I'm going to arbitrarily draw the methyl group at position 2 as a wedge, so CH3. I'm going to put the hydrogen in to help us determine R and S. I'm going to put the hydroxyl group at 3 as a wedge. Here's this hydrogen. So again, if we're numbering this, the carbon chain, we have 1, 2, 3, 4. What I'm going to do here is write 2 equals 3 equals. So if you can spend a minute or so and determine whether 2 is R or S and 3 is R or S. So in your chat function, just say 2 equals R or 2 equals S, 3 equals R, 3 equals S. When you have them both figured out, just put that as one line in your chat function before we move on. So it looks like the majority is 2S, 3R. So it seems like everyone's pretty clear on that. So S, R. My computer is falling asleep. So let me wake it back up. Okay, so we have that figured out. Now what I want to draw next is the enantiomer of this. So in the red pen here, I'm drawing the enantiomer or mirror image isomer. And all we're going to do, I'm going to leave the carbon backbone the same. So here's our 1, 2, 3, 4. I'm just inverting these wedges to dashes. Do that for the hydrogen as well. Since they're the mirror image, each one gets completely inverted. And since we've done it visually, we can say 2 equals R, 3 equals S. So these are enantiomers. So let's see who's the fastest typer here. So of these enantiomers, they have the same melting point, the same boiling point, the same NMR, the same solubility in, say, water. What's the only physical property that's different amongst these enantiomers? So we have optical rotation, specific rotation. So again, for enantiomers, specific rotation is the only thing which they'll differ. So one of these will have a plus rotation, the other will have a minus rotation. And the number after that is the degree at which it rotates the plane polarized light. So now what I want to do is draw the other. So we had, as we said, 2 to the 2 equals 4. We've drawn 2 of these products. These are enantiomers. Now we have to draw the other enantiomeric pair. And what I'm going to do to make life easy, so in black here, all I'm going to do is change one of these stereogenic carbons, and I'll leave the other one the same. So what I'm going to do is I'm going to leave 2 the same, and I'm going to change 3. So 2 will remain the wedge, and 3 I'll change to the dash. So I'll draw the carbon backbone. Put the numbers in. I said I was going to leave 2 the same. I was going to change 3 to the dash. So 2 is still equal to S. Now 3, since we flipped it, notice over here it flipped to S. This is going to be the S, 2S, 3S. So for diastereomers, at least one of the stereogenic carbons has flipped. And again, for enantiomers, they all flip in opposite directions. So if I want to draw the enantiomer of this, I'm just taking this one and I'm flipping it to the 2R, 3R. I think it's helpful to put these numbers in for the chain, if I draw them right, just so that you can see, if you take this stuff nice and slow and be logical about it, it's not that difficult. So we're flipping this one. It's going to be now the dash. Then we're flipping that one's going to be the wedge. And so what we end up with is 2 equals R, 3 equals R. And so what I want to do now is just show you in black pen here that these are diastereomers. So this 2 center is staying the same. The 3 is what's flipping. So because we flipped one of them, those are diastereomers. And then every other relationship, those are diastereomers. And these are diastereomers. So of these 4 here, there's 2 enantiomers. There's 2 pairs of enantiomers, excuse me. And then every other relationship, 1, 2, 3, 4, those relationships are all diastereomeric. And keep in mind, this was just the analysis of one of the cross aldols, where we have this other cross aldol situation as well down here. But that one only had enantiomers. This other self one had the same scenario with 2 pairs of enantiomers. So that's going to give sort of the same thing. What I want to do before we move off this slide and this white space here and over here is just a review of Newman and Fischer projections, so you don't lose track of that. Again, since you're not taking the ACS 256 exam, there's maybe a little less pressure on you, but some of you will still need to know this stuff if you're taking like the DAT or the MCAT or whatever. So I think it's helpful to review that. So over here first, on this side, for these 2 compounds, I want to draw Newman projections. And then for these on this side, I want to do Fischer as a review of these different projections. So for these Fischer projections, what we are going to look at, we're going to stick our eyeball in the plane of the paper, and then we're going to look down the C2 to C3 bond. So our eyeball is here, and we're looking down this sigma bond. So our front carbon, this group's going up. I'm going to abbreviate that aldehyde as CHO. Then we have this. So in your chat function, what should I write here? So Peyton says methyl, so CH3. So the hydrogen goes there. Now, if you're able to visualize this, that's great. If not, you probably want to have models for this. So when we're looking down this bond, here's the back carbon. Now this backbone is in the staggered conformation. So see how this bond here is up, which we drew up. This bond here is anti, so it's down, CH3. So we have this and that. So again, that's the staggered conformation. So what should I put here? You can type it in your chat box. So that's the hydroxyl group OH. And then there's our H. So let me just highlight that again. When we're looking down the 2,3 bond, I'm going to sort of bold this. This group is anti to that group. So again, we're looking down these two carbons, which is this axis here. So if the aldehyde up, we have the methyl group down. So in this Newman projection for the 2s, 3s, notice that the 2 did not change. So that's going to stay the same. That's the front carbon. Again, we're looking down this bond. The 3 did change. So what's changing is the stereochemistry of the OH. Over here, it was on the left. Now over here, it's going to be on the right. And that methyl group is still anti to the aldehyde. So any questions on converting sort of a flat structure into a Newman before we do the Fischer? Okay, so now for the Fischer projection, the way it differs from the Newman, again, in the Newman projection, you're looking down the axis of a bond. So C2 to C3, we're looking down that axis, which we've shown here. Now for the Fischer, we're going to put our eye in the plane, and we're looking at the 2 to 3 bond. Instead of looking down the axis, we're looking down the whole bond itself. And we set up here, the aldehyde is the most oxidized carbon. So in a Fischer projection, the most oxidized carbon always goes at the top. So we have our carbon backbone, which we draw as the vertical line. This is the most oxidized carbon, so it's going up top. This carbon here, this methyl at 4, goes down at the bottom. That's the least oxidized carbon. We said we have 1, 2 stereogenic carbons. So when you draw a horizontal line bisecting that vertical line, that means it's a stereogenic carbon. So that's carbon 2. And the next thing we draw is carbon 3. So this is what will maybe trip you up a little bit. When we convert this into the Fischer, we actually have to make sure that this backbone is not anti, but it's that it's basically C4 is eclipsing the C1. That may be a little bit confusing at this point, but C2 stays the same. C3 is going to be different than what you think it is. So when we're looking down this bond, again, here's 1, 2, 3, 4. 2 will stay the same. So when we're looking down that over here, we're going to draw CH3. Then that H is going to be here. See how this methyl and that hydroxyl group are sort of on that same back face? We do not draw the OH here. We're going to draw it over here. And again, the reason for that, you have to rotate around this bond so that this H or this aldehyde carbonyl and that methyl group are eclipsed to one another. So let me draw that sort of over here first so you can see. The C2 stays the same. This is what I mean by they're eclipsing when they're flat. So when we do that rotation, and again, we're looking down the length of that bond. So what you can see is that the OH now is here, that H is there, this methyl is there, that H is there. So again, the things on the horizontal are coming out towards you. The things on the vertical are receding away from you. Hopefully that's clear enough for now. Let me draw the we're going to draw this one as the diastereomer. Again, you have to do that rotation. So essentially what we're doing, we're leaving C2 the same. We're rotating around this bond, so the OH is going to flip over to there. So see how in this sort of flat anti, the CH3 and the OH are like opposite. In the Fischer projection, they're actually the same. And again, some of you are going to be taking these pre-professional exams and you're going to see the Fischer projection, so that's why I wanted to review that. Questions before we move on from this slide? You don't see any questions in the chat, or again, you can unmute yourself and ask a question. So what I would like to do now is just do some problems from the book real quick. So let's do 21:17. So it's basically giving you this aldehyde and it says draw the condensation products when treated with sodium hydroxide. So when you're only given one carbonyl functionality, it's going to be a self-condensation. So they're treating it with sodium hydroxide and water. So because we're in the presence of base, we're going to generate an enolate. And so how do we figure out what the products are? Again, I draw these things a certain way because it helps me keep track of the bond that's forming and what stereochemistry is in the product. So just down here, I'm going to write electrophile. The electrophile is just simply the compound itself. And then the enolate, we're enolizing the alpha carbon. So sodium enolate. So let me just put this H in there so you see it. So this enolate in particular, if we're looking at this carbon, and we assign priority of carbon versus H, the carbon is 1. Oxygen versus H, the oxygen is 1. They're on the same side of the alkene. So this is the Z enolate. Let me just show you what forms as well. This also forms and you have no way of controlling it at this point. We do the same analysis, 1, 1. Now they're on opposite faces. This is called the E enolate. So you're forming both of these enolates in equal mixture. Each of those is attacking the electrophile. And so if we draw the arrows of that, again, this collapses. That's the alpha carbon. We're forming a bond between the alpha carbon, and this is the new beta carbon. So again, that's a nucleophilic addition. This oxidation state decreases from 2 to 1. So I'm just going to draw the neutral product here. This is the new beta carbon. This is the bond that's formed. There's the alpha carbon, and we need 1, 2, 3. 1, 2, 3 to complete the chain. So again, the new bond is always between alpha and beta. The beta carbon decreased in oxidation state from 2 to 1. We end up with 2 to the 2 or 4 stereoisomers. And again, just a little bit of a deeper explanation of why there's 4. You end up with different enolates, and those enolates can attack either face of the carbonyl. So we've seen before for Ingold Pralog, sp3 hybridized carbon can be R or S. But we really haven't seen anything for sp2 hybridized carbon yet. This is an sp2 hybridized carbon. This also can have rules for Ingold Pralog. This molecule itself, as drawn, does not have a stereogenic carbon. But you can see, again, if I put this little dot here, in the product, it ends up as a stereogenic carbon. So what we say is that that carbon is prochiral, that it can become a stereogenic carbon in the product. So what we can do now, we can assign the face that you're looking at, where this pen, if it attacks that carbon from this face, we can assign Ingold Pralog designation to this using the following. Again, you're looking at the atomic number. Oxygen is going to be 1. Carbon is 2. Hydrogen is 3. So from this face that we're looking at, we're going in this direction. So that's counterclockwise. So that's called the psi face, SI. If you were looking at the other face from below, as in the nucleophile is coming up from below, or if I just redraw it the other way, we have 1, 2, 3. That face, which is clockwise, is called the re face. So for sp2 hybridized carbon, you can have re or psi. So if you look at all these possibilities, this is how you end up with 4. The Z-enolate can attack the re face, it can attack the psi face. The E-enolate can attack the psi face or the re face, and so total, that's how you get 4. Again, your book may not go into that, but that's an explanation of how you get so many. Questions on 2117A? So again, this was predict the product. Let's go to (2119). And this one says, identify reagents that can be used to produce each of the following compounds via an Aldol reaction. So this one, we're given the product and asked to draw the reagents or reactants. So this is our product. This arrow means retrosynthesis, meaning what reagents make that. So we're thinking backwards at this point. And so how do we approach this type of problem? Here's the carbonyl functionality. We have an alpha carbon. We have a beta carbon. Now, if we go the other way, we have alpha prime, we have beta prime. From what we've just seen, the aldol product is a beta hydroxycarbonyl. So in this product, that is the bond that we have made. So the enolate has to come from alpha prime. The electrophile has to come from beta prime. And again, because this is the product, beta prime has undergone a reduction. If we count now, beta prime is at oxidation state 1. So in the electrophile, it has to be at oxidation state 2. So maybe in your chat function, can you write the name of what the electrophile is going to be? I'm going to take a sip of Red Bull. Anybody? So Jack Patterson says formaldehyde, and that is the correct answer. So again, there's the electrophile. Formaldehyde, it's at oxidation state 2. It's reacting with this ketone. I haven't drawn it in the enolate form, but this is what we start with. If we look at A, remember A we said, or excuse me, alpha. There's no hydrogens on alpha, so that's non-enolizable. So alpha prime is enolizable. The enolate form would be that. So we've enolized, that's supplying the electrons to attack formaldehyde, and that's how we end up with this product. So maybe what I'll do on the second half of this sheet here, so how do we control aldol reactions? Again, when you run a reaction, you don't want to produce 12 different things because that's a mixture and it's like very hard to separate those things out. So how do you control an aldol reaction? So you can start with using an electrophile that is non-enolizable. And so we've seen that up here with formaldehyde. Formaldehyde is an aldehyde. It does not have any alpha carbons. So this cannot form an enolate. And we've seen from this species, since one of these alpha carbons is non-enolizable, that means the only enolate that can form is from this side. So we only get one enolate, and that can only attack the electrophile, so we're basically controlling it to get one product. So what are some of the other non-enolizable aldehydes? So we saw formaldehyde. This compound is called pivalaldehyde. It has an alpha carbon with 3 carbons. It's non-enolizable, so it can only act as an electrophile. And then another one is benzaldehyde. So the alpha carbon bears no hydrogens. So that these are all non-enolizable aldehydes. So for example, if we had the following, if we took this ketone, which is called propanone, plus benzaldehyde, sodium hydroxide, and water, this will still undergo a self-condensation. So we can't control this from undergoing a self-condensation. It will do that. So we're basically, by using a non-enolizable aldehyde, we're limiting the number of self and cross ones that we can form. So if this is our enolizable moiety reacting with the electrophile, the product of that cross condensation, this is the bond we form right there. So there's the alpha, there's the beta carbon, so there's the bond we formed. So enolate, electrophile. So the electrophile bearing the carbonyl, highlight in blue, that always ends up at the beta position. So the other thing, like I said, that we'll get from this, I just want to show it just so you see, is the self-condensation of the 2-propanone. So this reacting as both the enolate and the electrophile will form that. But you can see by limiting one of them to non-enolizable, we've significantly reduced the number of products. Of course, this will be a stereogenic carbon. So instead of 12, at this point, we would end up with 3. So the enantiomers of this and plus that would give us 3. Any questions before we move on from this one? So we're going to do one more Aldol reaction before we move on to the higher oxidation state Claisen reaction. So the intramolecular Aldol reaction leads to a cyclization, meaning that we're forming a ring. So let's look at the following substrate. So we're going to take this diketone, the presence of sodium hydroxide, water, and then heat, and I'm going to explain what the heat is there for. So we know that an aldol reaction forms a beta hydroxycarbonyl. So what is challenging about this particular system here? So if we identify, we have this alpha carbon, which is the same as that. The molecule is symmetric. Then we have these methylenes, which are both alpha prime. So the CH3 groups are equivalent. The CH2 groups are equivalent. Under these conditions, we're going to form the thermodynamic enolate, which is going to result from deprotonation of the alpha position that has the least substituted or the least number of hydrogens. So we talked about this, I think, last week. Alpha has 3 hydrogens, so that would be a kinetic enolate. Alpha prime has 2, that's the thermodynamic enolate. The reason we have to identify that first is that's the formation of the nucleophile. So let's go ahead and draw that. And it doesn't really matter which alpha prime we deprotonate from. I'll just show this one. Again, this is an acid-base reaction. We're under equilibrium here. So this is formation of the thermodynamic enolate. So I've done sort of redrawn this chain for a specific reason. So we've deprotonated this alpha prime here. Now what I want to do is, because this is acting as the nucleophile, alpha prime, I'm going to number that 1, 2, 3, 4, 5. In these intramolecular aldols, the nucleophile and the electrophile are within the same molecule. So we are forming a bond between carbon 1 and carbon 5. So the enolate will collapse. We form a bond between carbon 1 and 5. That means we form a 5-membered ring. That's the nucleophilic addition. So I'm going to write at this point from alpha prime, a 5-membered ring. So coming off carbon 5, we have the methyl group that does not change. Now we have this new beta carbon, so alpha, beta prime, that underwent a reduction. So there's the new bond we formed. We do a proton transfer with water. That protonates the beta position. So here's our beta hydroxy carbonyl. So I mentioned that the reaction also has heat. So one thing that Aldol reactions can do, and this sort of simplifies things, because we said there's a stereogenic carbon, there's a stereogenic carbon, so 2 to the 2 equals 4. Now in the presence of heat, notice the arrow changes. This is a one-way arrow. These reactions will do an elimination between the alpha and beta carbons. So we're losing H2O. That's the elements of water. So this is called the dehydration. So really, how do we view that? It's hydroxide abstracting this proton. We form the pi bond and we eliminate hydroxide as well. So now this is a alpha beta unsaturated carbonyl. So Aldol reactions can be intermolecular, that's 2 different species, or intramolecular, where there's what happened to the methyl group. It's still there. I forgot to draw it. Thank you. So intramolecular is where the nucleophile enolate and the electrophile are within the same molecule. They end up forming a ring. Then in the presence of heat, you do a dehydration between the alpha and beta carbons to install a double bond. Any further questions on that? So what I would like to do now in the last 5 minutes is just give you an introduction to the next reaction that we're going to learn, which is called the Claisen reaction. And the way this is different if you look at this bond that you formed between alpha prime and beta prime here, this beta prime carbon is at oxidation state 2. Then it gets reduced to oxidation state 1. In the Claisen reaction, you're starting at oxidation state 3, and it gets reduced to 2. So instead of ending up with a beta hydroxy carbonyl, you end up with like a beta keto carbonyl. So let's go ahead and look at just an introduction to that, which we'll pick up more on Wednesday. So again, this is the Claisen. Claisen condensation. We're going to look at the simplest case here, this ester. Again, it's a self-condensation. This molecule is ethyl ethanoate. One thing I want to point out, the base that we use, see this base here, ethoxide, that base has to match the alcohol portion of the ester. So whatever this alcohol portion is, that base has to match it. I'll explain more why that is on Wednesday. So you run these in the presence of the matching alcohol, so sodium ethoxide and ethanol. Then at the end, you have to do an acidic workup, and we'll talk about that, why that's important as well. So briefly in the last couple minutes, let me just show you if this acts as the electrophile. Let me draw this enolate here. So this is an ester enolate. So here's our alpha carbon. Again, that's reacting with itself. We're at oxidation state 3. This is going to become the beta carbon. This will collapse to form the alpha beta bond. So this is a nucleophilic addition. This is the bond we just formed. So there's our alpha carbon. Here's our beta carbon. Notice it went from 3 now to 1, 2. So that's a nucleophilic addition. This then collapses to reform the pi bond, and it eliminates out the ethoxide. So we're now forming a carbonyl. So this ends up at oxidation state 2. There's your alpha carbon, there's your beta carbon. I'm sort of out of time at this point. So let me just say the reason that this is here as a separate step is because in the reaction mixture, you form some very acidic protons. So before you actually end up with the final product, this will abstract these, and then you have to neutralize it or adjust the pH to acidic with weak acid. I'll go through this again on Wednesday, but basically what you're ending up with for a Claisen is a beta keto ester. So the Claisen has an increased oxidation state at the beta carbon. So we'll pick this back up on Wednesday. This was a self-Claisen. We'll look at cross-Claisen. Then we'll look at the intramolecular Claisen called the Dieckmann reaction. So I'll be online tomorrow at 4 p.m. for office hours. I'll do the same setup probably. Please give me some feedback if this worked or not. You can send me an email or something through Canvas is fine. But other than that, if you haven't done so already, please start doing your Wiley Plus assignments. Your exam 3 is next Monday, and I'll explain more about that on Wednesday as well. But other than that, I'm going to go ahead and sign off at this point. Again, we'll see you either tomorrow or Wednesday.